Hello, you are welcome to our SHS 3 Core Mathematics lesson. This is brought to you by the Center for National Distance Learning and Open Schooling. My name is Lucy. In our previous lesson, we learned about differentiation of algebraic functions. In this lesson, we want to look at rates of change. By the end of this lesson, you should be able to A. Find the rate of change and small changes. You should also be able to find the maxima and minima values and points. Now let's go into the details of this lesson. If a quantity y depends on and varies with a quantity x, then the rate of change of y with respect to x is dy dx. That means, for example, the rate of change of pressure P with respect to height h is dp dh. Rates of increase have positive dy dx, and rates of decrease have negative dy dx. Chain rule can be applied to solve questions involving rates of change. For example, to find the rate of change of volume of a sphere with respect to time, we'll have dv dt is equal to dv dr multiplied by dr dt. Where r is the radius of the sphere, v is the volume of the sphere. Before we start the rate of change, let us quickly revise the chain rule. That is how to differentiate a composite function. We call this differentiation of a function of a function. To differentiate a function of a function, for example, y is equal to ax plus b all to the exponent n, we can do a chain differentiation. That is, we introduce a third variable u such that y is equal to u, or y is a function of u, and u in turn is a function of x. That will be written as dy dx is equal to dy du multiplied by du dx. This is called the chain rule. Let's take an example. Differentiate y is equal to 3x plus 2 all cubed with respect to x. Let's take the solution. We are given that y is equal to 3x plus 2 all cubed. To differentiate this function, we shall make some substitutions. Let u be the function that is inside the brackets, that is 3x plus 2. This means that we can rewrite y is equal to u cubed. Now we will differentiate u and y separately. So du dx is equal to 3 and dy du is equal to 3u squared. Now using the chain rule, which is dy dx is equal to dy du multiplied by du dx, we will have dy dx is equal to 3 multiplied by 3u squared. When we simplify that, dy dx will give us 9u squared. But remember that u is equal to 3x plus 2. That was what we substituted for u. So we will replace this. Therefore, dy dx is equal to 9 into bracket 3x plus 2 all squared. I hope you understand. Good. Let's take another example. Differentiate y is equal to 2 minus 3x all squared with respect to x. Let's take the solution. From this question, we have y is equal to 2 minus 3x all squared. We will substitute u for 2 minus 3x. So let u be equal to 2 minus 3x. Then we can rewrite y as u squared. Now we will differentiate u and y separately. So the u dx will give us negative 3. And dy du is equal to 2u. Using the chain rule, dy dx is equal to dy du multiplied by du dx. We will replace the various items. And that will give us dy dx is equal to 2u multiplied by negative 3. But remember, u is equal to 2 minus 3x. And so replacing that, we will have dy dx is equal to 2 into bracket 2 minus 3x multiplied by negative 3. When we simplify that, we will have negative 6 into bracket 2 minus 3x. Here we can decide to expand. Therefore, dy dx is equal to negative 12 plus 18x. Wow. Good. Let us continue. I believe this will get you ready for questions on rates of change. In fact, what we have done is just to review certain things so we can work on rate of change. Let us now move to questions involving rate of change. We want to look at some examples. Example 3. The radius r centimeters of a spherical balloon is increasing at a rate of 0.5 centimeters per second. At what rate is the surface area increasing when the radius is 4 centimeters? Let's take the solution. Let the surface area of a spherical balloon be A, and that is given by 4 pi r squared. You remember we found the surface area of a sphere in one of our previous lessons on mensuration 2. And we have the surface area of a sphere to be 4 pi r squared. So we will differentiate this with respect to r. That means the ADR is equal to 8 pi r. Now differentiating the surface area has given us 8 pi r. But we know that the ADT is equal to the ADR multiplied by the RDT. That is from the chain rule. We have been given R. The value of R is 4 centimeters. And we have also been given the RDT, which is 0.5 centimeters per second. Now we shall substitute the given information into our differential. That would give us the ADT is equal to 8 pi multiplied by 4 multiplied by 0.5. When we simplify this, it gives us the ADT is equal to 16 pi square centimeters per second. You can decide to replace pi, but as it is, we want to leave the answer like this. Good. I hope you were able to follow through with me. Let's take another example that is like the previous one. The radius of a circle increases at a rate of 0.4 meters per second. Find the rate of increase of the circumference. I want you to take pi to be equal to 3.142. Let's take the solution. We have been given the r dt, and that is 0.4 meters per second. Now we want to find the c dt, that is, we want to differentiate the circumference with respect to time. The circumference of a circle is given by 2 pi r. C is equal to 2 pi r, where c is the circumference. So we shall differentiate the circumference with respect to the radius. And that will give us the c dr is equal to 2 pi. Now we will use the chain rule, and then that will give us the c dt is equal to the c dr multiplied by the r dt. So the c dt is equal to 2 pi and then multiplied by 0.4. When we simplify this, it will give us 0.8 pi. But in the question, we were given the value of pi. That was 3.142. So we replace the value of pi, and that gives us the c dt is equal to 0.8 multiplied by 3.142. When we simplify this, it will give us the c dt is equal to 2.51 meters per second. When we simplify this, it will give us the c dt is equal to 2.51 meters per second. Good. I want us to take another example. The radius of a sphere is 6 centimeters, and it is increasing at a rate of 0.25 centimeters per second. At what rate, in terms of pi, is the volume of the sphere increasing? Let's take the solution. We have been given r, the radius, and that is 6 centimeters. The r dt has been given, and that is 0.25 centimeters per second. Now we want to find the v dt. The volume of a sphere is given by v is equal to 4 divided by 3 pi r cubed. Remember, we learned that in mensuration 2 also. The v dt therefore becomes 4 pi r squared. That is when we differentiate v. Now we would apply the chain rule. So using the chain rule, we have dv dt is equal to dv dr multiplied by dr dt. So dv dt is equal to 4 pi r squared multiplied by 0.25. We simplified that to get dv dt is equal to pi r squared. But we were given the value of r. We were told r is equal to 6 centimeters. So dv dt becomes pi multiplied by 6 squared. And that will give us 36 pi cubic centimeters per second. Therefore, dv dt is equal to 36 pi cubic centimeters per second. Great. We are taking another example. A circular ink blot has a radius of 2 centimeters. At what rate is the area increasing with respect to the radius? Let's take the solution. We want r centimeters to be the radius of the ink blot, and a squared centimeters the area as well. Now, since the ink blot is circular, its area is given by a is equal to pi r squared. The rate of increase of a with respect to r is the r is equal to 2 pi r. Now, if r is equal to 2 centimeters, then the r is equal to 2 pi multiplied by 2, and that will give us 4 pi centimeters. Therefore, the rate at which the area is increasing with respect to the radius is 4 pi centimeters. I hope that is clear. Good. Now let's extend our lesson to small changes. Consider the two variables x and y. If x increases by a small change, delta x, then y increases by a corresponding small change, delta y. That means that delta y, delta x will approximately become dy dx. We will write this. We say as delta x approaches 0, delta y, delta x approaches dy dx. Now the small arrow there is what I'm reading as approaches. Therefore, we will multiply through to get delta y is approximately equal to dy dx multiplied by delta x. Let's take an example. The side of a square is 5 centimeters. Find the increase in the area of the square when the side expands 0.01 centimeters. Let's take the solution. Let the area be a centimeters squared and the side x centimeters. Then a, which is the area, becomes x squared. Remember, the length of the area of a square is L squared. And here we are representing L with what? X. So the a dx, that is when we differentiate a with respect to x. The a dx is equal to 2x. But delta a delta x is approximately equal to the a dx. Therefore, delta a is approximately equal to the a dx multiplied by delta x. If x is equal to 5 centimeters as given in the question, then the a dx will be equal to 2x and delta x is equal to 0.01 centimeters. So delta x is equal to 2 multiplied by 5 multiplied by 0.01, and that will give us 0.1. The increase in the area is therefore 0.1 squared centimeters. Good. Now we shall discuss how differentiation can be used to find the maximum and minimum values and points of a function. Because the derivative provides information about the gradient or slope of the graph of a function, we can use it to locate points on the graph where the gradient is 0. Stationary points. Stationary points are points on the graph where the gradient is equal to 0. There are 3 points that are known as stationary points. There are 3 types of stationary points: maximum, minimum, and then point of inflection. The three are illustrated in the diagram you can see. So we have the minimum, we have the maximum, and then we have the point of inflection. Good. Let's take an example. Find the coordinates of the stationary points on the graph y is equal to x squared. Solution. We know that at stationary points, the y dx is equal to 0. We call the stationary point the point at which maybe a particle is at rest. Since the gradient is 0 at this point, we will differentiate and equate to 0. So by differentiating, we get the y dx is equal to 0. Therefore, the stationary points on this graph occur when 2x is equal to 0. That is when x is equal to 0. Now, when x equals 0, y is also equal to 0. That is when we replace the value of x by 0. We get y also to be 0. Therefore, the coordinates of the stationary point becomes 0, 0. In this case, it is only one stationary point that is a minimum. The graph of y is equal to x squared is U-shaped with its lowest point at the origin. Now, let us look at the second differential. The second differential coefficient is given by the square y dx squared. If y is a function of x, then the y dx is also a function of x, or a constant term. Hence, we can differentiate the y dx with respect to x. This gives the second differential coefficient, which is written as the square y dx squared. The squared y dx squared is sometimes written as f prime prime of x, where y is equal to f of x. Let us take a quick look at maximum and minimum values of a curve. The curve, you can see, has a maximum and a minimum point. This leads us to the preferred method for determining the local maxima or minima for some functions. 1. Differentiate the function f of x to obtain f prime of x and f prime prime of x. 2. Solve the equation f prime of x is equal to 0 for x to get the values of x at potential minima or maxima. 3. For each x value, I determine the value of f prime prime of x at the x value. 2. Decide if you have a minimum or a maximum. How do we decide? A. At all local maxima, f prime prime of x is less than 0. In other words, the second derivative is less than 0. B. At all local minima, f prime prime of x is greater than 0. C. If f prime prime of x is equal to 0, we will have what we call the point of inflection. Good. I want us to take an example on this. Example 9. The equation of a curve is y is equal to x squared minus 6x minus 12. Find the minimum value of y. Let's look at the solution. We have been given y is equal to x squared minus 6x minus 12. When we differentiate this, we'll have dy dx is equal to 2x minus 6. But at the turning point, dy dx is equal to 0. So we would say 2x minus 6 is equal to 0 and solve for x. So 2x is equal to 6 and x is equal to 3. Now we will put x is equal to 3 into the relation for y. That will give us y is equal to 3 squared minus 6 multiplied by 3 minus 12. That is, wherever we see x, we put 3. When we simplify that, we will have y is equal to 9 minus 18 minus 12, which gives us y is equal to negative 21. Therefore, the minimum value of y is negative 21. I hope you understand. Good. For what value of x is y is equal to 2x cubed minus x squared minus 8x plus 4 a maximum? Let's take the solution. We have been given y is equal to 2x cubed minus x squared minus 8x plus 4. We'll differentiate this to get 6x squared minus 2x minus 8. So dy dx is equal to 6x squared minus 2x minus 8. But at the turning point, dy dx is equal to 0. So 6x squared minus 2x minus 8 is equal to 0. We'll simplify this by dividing through by 2. And that will give us 3x squared minus x minus 4 is equal to 0. Let's factorize. So when we factorize, we'll have 3x minus 4 in one bracket and x plus 1 in another bracket, all equal to 0. And solving this will give us x is equal to 4 divided by 3, or x is equal to negative 1. The turning point occurs at x is equal to 4 divided by 3, or x is equal to negative 1. Now, when we take the second derivative, we will have the squared y dx squared is equal to 12x minus 2. Then we substitute the x values in terms into the second derivative. So when we take the x value, that is 4 divided by 3, we have the squared y dx squared is equal to 12 multiplied by 4 divided by 3 minus 2. Simplifying that will give us the squared y dx squared is equal to 14. Now this value would not be used. We are only going to check the sign of this value. A positive value means it is a minimum turning point. Again, we will take the second x value, which is x is equal to negative 1. Substituting that into the squared y dx squared gives us 12 into bracket negative 1 minus 2. When we simplify that, we will have the squared y dx squared is equal to negative 14. Again, we check the sign. The sign is negative, and so we conclude that this is a maximum point, a maximum turning point. Therefore, y has a maximum value when x is equal to negative 1, because it is x is equal to negative 1. It is negative 1 that we place in the second derivative to get a negative value. Well, I hope you understand. Good. In this lesson, we have learned that if a quantity y depends on and varies with a quantity x, then the rate of change of y with respect to x is dy dx. We have also learned that the stationary points are points on a graph where the gradient is 0. Well, students, we have come to the end of today's lesson. In our next lesson, we will continue with calculus, where we look at integral calculus, that is integration. Until then, it's goodbye.